expect it to be and solve the constant to get like the true W.
Yes, I was.
I was on Thursday.
We have
How many
Yeah. Oh.
more than that.
Okay.
Even the margin, like I actually have to use the formula.
Yeah.
And it was like, I think
it was like radical super.
I think when they did it, they literally just they were like, oh. Yeah, so even if you can't go to margin, I think you're like, oh. Do you see the board?
Yes.
So, just a recap of logistics, where we stand. Saturday, 4:20 exam. I think it's 10 a.m. We'll announce the room, probably WPH. This is gonna be roughly 2 problems, roughly the same kind in the homework. If you get it right the first time, it can take 1 hour. If you need to debug things a lot, it may take 3 hours, who knows. So it will be 6 hours exam, but the people who get it straightforward right will be done in 2 hours. Thursday lecture, that's, what is it, 11? This Thursday. That will be Professor Javed Aslam. He's a spectacular teacher. You shouldn't miss his lecture. I don't know what he's gonna teach, to be honest with you. I told him we're gonna do Nearest Neighbors. Just in case, I'm gonna start that today, because the homework is about that. And if Jay Aslam chooses to do so, that'd be great. If he chooses to do something else, he knows a lot of things, so he can do something fun. That's up to him, but he's a spectacular teacher. Please, what is it called, trace? Like I said before, be honest, say the good things and the bad things, but please do them. Please go online and say, I really didn't like Virgil, or whatever. You know, I like this course, I didn't like this course. Here's what should be done better. Here's which is too much, it's too little, you know. Say in your own words what you feel like. And there will be a homework final deadline. This is gonna be strict, not like the deadlines we had the whole term, okay? This is gonna be an actual deadline. My guess is that that will be 4/22. PAs will figure that out, but after that, maybe 23? You know? So as long as they can, there will be some deadline that after that you can add them homeworks. We'll announce it, so make sure you do the best you can by then. All right. Yes?
What about the math problems?
Yeah, I'm grading those, takes me a long time.
Is there a hard deadline for that?
The math problems in the past,
Yeah.
those are, if I get to grade them and it's not there, it's, you can submit it after that. The moment I grade homework 3 problem 2, I'm gonna look at everybody what they submitted homework 3 problem 2, and that's gonna happen. I'm already did some of them. I didn't put grades in the grade sheet, but I looked through some problems, homework 1 and 2. And this week I'm going away for a few days, so add something here, Virgil's office hour. Next week. So I won't be today at office hours Wednesday and Thursday. So if I grade that problem and it's not there, it's over. Okay? The latest homeworks don't have math problems, right? So we don't talk about homework 1, 2, 3. Is that it? Like, I hope you guys done with homework 1, 2, 3 by now. Yeah. Okay. We are, as you know, we are lenient on homeworks, both on the math and on the code. Like if you have the right results, if you have the right math idea, you're gonna get a point. We're not gonna be picky on those problems. Did we figure out the spheres n plus 1 thing?
Partially.
Partially. All right. Okay. Before I keep going with kernels here, we had a discussion yesterday at office hours. And I keep thinking about that. And I don't think we tried this, but I want you to hear me out what I'm thinking about. Here's that SVM plane. So it's here. Right. And then I have a bunch of presumably some minuses here, and I have some pluses here. And I'm going to have some errors too. I'm talking about your homework 7. In reality, of course, there'll be some pluses on the wrong side, some minuses here, and some troubles. I'm also going to consider this normal to the plane. This is the vector W, right? The plane is Wx plus b equals 0. That's the separation plane. But the vector W is the normal, right? So now, what does this mean? Of course, it means this in this direction, Wx plus b is big. And this means Wx plus b is small. That's the idea. That's the negative side, that's the positive side. It's conceptual, right? So now, if you remember what you have to do in homework 7, in SFO, there's some blah 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 initialization. I mean, that's not trivial, but I don't want to talk about it. And then you say, here's a loop, right? Select alpha I, then select paired alpha j. So that's the second selection depends on alpha I, right? And then figure out there's a constraint that says alpha I yi plus alpha j yj. That's a constant. That's because the other alphas are fixed. So once I pick a pair, either there's some or there's difference, because y's are plus and minus 1 here. Either there's some or difference is constant. So subject to that constraint, I have to maximize the function that's in alpha I and alpha j right over there. The quadratic function. Sum of the alpha I. I have the formula here. So what was the formula for the dual sum of the alpha I plus something like sum of the alpha I, alpha j, yi, yj, xi, xj? Then you can check to see if this is the right formula. Something like this. Right. So now, of course, this is a quadratic form on alpha I and alpha j. Let's pick those different indices here. So this is A and B, alpha A, B, A, B, A, B, because I already pick an I and J here. Because everything is fixed except for the alpha I and alpha j, I have a quadratic equation maximized subject to some constraint. And of course, 0 smaller than alpha I, alpha j smaller than 0. That's the idea of SMO, right? Pick two variables, get the constraint, and subject to that constraint, maximize the platform. And loop until you're done looping. So that's where it is done, nothing new so far. But somebody asked me yesterday, Max actually, well, how do we start this thing? Where do we start? There's something in the note, where do we start? At 0, right? Does it make sense to start at 0?
All of them are 0, all alphas.
Yeah. Does it make sense or not?
Last time you said that random values should be okay.
Right. I've changed my mind. No, I'm just saying. Why random or why 0? Let's hear some speculations.
With random, you might have less far to move, you might have more wiggle room, but it is harder to make it to guarantee that you're meeting the constraint for the sum.
Right. You mean this constraint right here? The sum of The constraint was sum of alpha I, yi has to be 0. That's constraint.
Yeah.
Okay, so what else? Yes.
I remember we talked about if you are expecting to end up with the majority of your alpha 0, then it'll leave the support for 4.7.
It's an important point. That's what I want to say. If we're expecting most of the alphas to be 0 at the end, are we? Because we expect a clear separation. Both data sets that you have, the span base and the MNIST, most of the points are easily separable, which means even though you have some errors, most of the points will be far away. Like as a visualization, you see the big clusters here and here, it's easy to separate. You see something, let's see, it's all like in a mess, then that's hard to separate, right? If we expect most alphas to be 0, wouldn't it be better to initialize them to 0? As in, suppose MNIST has 60,000 or 70,000 images, right? Out of 70,000 images, suppose 3/4 of them, I don't know, 55,000 or so, have alphas equal 0. Then would it make sense to start, if I initialize it with random, then most of them will not be 0, which means the algorithm SMO is supposed to bring them to 0 somehow, right, by the end. If in the end we know we expect them to be 0, right? Are you guys following me? So how many of these iterations do I need if I have 70,000 alphas and I initialize them with random values? And then I run through this loop. How many times I have to run through it to bring all these 55, 60,000 alphas to 0? I'm just saying, it may take a long time. What else? So I think people have succeeded with them 0. I'm not saying if you don't initialize them to 0, it doesn't work. But I'm saying zeros is probably closer to where the solution is, except there's a caveat to that. Yes?
If you initialize all the alphas to 0, you are already satisfying the KKT conditions.
I'm not worried about the KKT conditions, and it can be all satisfied, the constraints. Remember the constraint? So the plan is, this is not part of the algorithm. This has to happen, but the other constraint was yi times wx plus b, right? Has to be bigger than 1 minus set I. These are the ones that are going to be violated the most, because these constraints have to do with balance the plane. The positive force have to be equal to the negative force, right? The plane has to be in equilibrium. If the plane is a little bit out of balance, this won't be 0, right? But the plane could still be quite good. A separating plane could be roughly in the right position, just not equally pressure from both sides. However, what is this? This is the correct classification. This is the separation, right? This tells me that the plane is in a correct position. I'm saying any initialization that doesn't take into account classification, which is both zeros or random, right? When you initialize all alphas to 0 or to random, can we all agree we've got ourselves a random plane? We didn't take any plus and minus into account. We just get here some random initialization, which corresponds to a random plane. That plane could be this way, this way, this way, anywhere in here, right? A random plane would probably violate most classification constraints, right? A random plane, it's random to everybody, so it's gonna assign points randomly to plus and minus. That's gonna be 50% error, right? Like if I assign points plus and minus at random, I'm probably gonna get something like 50-50 right? So I'm saying I'm gonna violate a lot of these constraints, which is where SMO starts. The criteria for picking alpha I has to do with the most violated constraints, which is probably gonna direct from here. So my point from today, which I'm finally making now, is wouldn't it be nice if I put a plane initially not in a random position? So here's what I mean. I know there's gonna be a lot of tuning that's concerning the points close to the plane, I'm expecting SMO to have to work in here to figure out exactly where this plane is, to figure out all these points which have alphas 0 and which ones have alphas positive, right? The alpha 0 is outside the margin, alphas positive, so these are the margin, right? Alphas positive is inside the margin. That's where SMO comes into play. Figure out exactly for these points, well, it's in and out, rotate the plane a little bit, do whatever. But it would be very nice if SMO wouldn't have to worry about the points that are already far away. So again, in an easy classification problem, like you guys have in this homework, both data sets are very easy to classify. You run any algorithm, you get 95% accuracy. Right? In such an algorithm, can I identify most of the points that are way far from the margin in both sides? And say, I would like SMO to not deal with those because I already know that alphas are 0. Right? I'm talking about stuff in here that's clearly a plus region, and this is clearly a minus region. And I would like to say, before I even start SMO, hey, those are 0, don't change them. Those are 0, don't change them. And put a plane somewhere where it at least classifies those clear, easy regions. And say, figure out the middle part, which is only 20% of the data. Again, if I have a complicated data set like 20 news group, it's hard to get 90% in there. So probably the middle part is a lot of that data set. But in the MNIST or spam based, these are big regions, right? The stuff that's easily out on the plus side or minus side, it's quite a lot of the data. Hands up, who's with me? I don't have an answer to this question. I just posed the question, okay? Is there a way to put a plane somewhere in a reasonable position? Or equivalently, decide those alphas are 0s and we don't want to worry about them too much. So in other words, kind of not consider them here, at least in the beginning. Tell SMO, hey, in the beginning, I have these big regions which I'm pretty confident about. When you select the alpha and alpha j, leave these regions in peace. And just worry about the middle part. That will prevent the following from happening. Suppose I initialize this to 0, right, all of them. I get a random plane. I get then an alpha I and alpha j. What's the chance that some of these alpha and alpha j will end up being in the regions that are pretty clear to me, like all set? It's quite high because I think those regions are big. In spam base, I think this is like 80% of the data, maybe more. So when I pick the first alpha alpha j, I'm going to pick in here. Now in here, alpha is already 0, which is probably its final value. Probably. I'm not saying all points will have to be nailed at 0. Maybe some of those end up close into the margin, but most of these points and these points should probably have alphas equal 0. So now if I pick one of them in round 1 of SMO, what's going to happen here when SMO says, okay, get your alpha j, set the constraint, and then maximize this quadratic form? Initially it's 0, and after the first step will be what? Non-zero, right? Because if you look at this form, if you start with 0, as soon as you maximize this quadratic form, that's not going to be 0, 0, right? So then it's going to play with all kinds of random points, move them away from 0, which means later on we'll have to bring them back to 0 somehow. If I'm to get, if my intuition is correct about data here. So that was my point, is if I could kind of guess this plane roughly where it is separable, it doesn't have to be very accurate. It could have a lot of errors here. But I want to eliminate these clear, easy regions from SMO to have a less work. And then maybe after 100 rounds of SMO, I could include those points just in case SMO needs to look at some of them. But once the plane is pretty good, I'd say if somebody here violates a constraint, it qualifies as an alpha I, okay, then consider that point and optimize for it. Hands up who's with me. So can you put the plane in a reasonable position somehow? How?
You can do the linear regression model and then calculate the values of alpha.
So if I use a linear regression, I mean, I'm not saying that's good. I'm saying if I use something, anything, W is the regression coefficients, right? Very small values will be probably the alpha 0. Very high values will be probably the alpha 0. I think that's an idea worth playing for. If at least if your first SMO try doesn't work very well, you know, here's an idea to try. Is that what you were doing yesterday? Maybe I didn't understand very well.
No, I
kept thinking about
yesterday I
it.
said linear regression. You want to do logistic classification, not regression, because it's a classification problem.
Yeah, but that I'm not worried about the objective of that regression function, whether it's a square objective or a likelihood objective, because that's the biggest difference. You still get the W coefficients, and Wx plus b is a small side, and Wx, both regressions have an internal score. The difference is they apply logistic or not, which doesn't matter here. If you can get enough confidence to say, let's not worry about these alphas in the beginning, and let's not worry about these alphas in the beginning. You should try to see if there's a gap in there, like a massive gap, because that's what you want, to have this massive margin gap that will give you the sense, okay, these are going to be zeros anyway. It's pretty similar with active learning, right? Active learning will end up focusing on points close to the plane. Just in here, it's a very geometric focus. That was yesterday at office hours. I expect some people will start working on support vector machines now, right? Is that the plan? Yeah, we should start working on these support vector machines. And I'm going to talk a little bit about kernels, a little bit more about kernels, and a little bit more about KNN. And KNN will finish it some next time. So here's where we were last time with kernels. We talked about a few kernels, and we talked about theorem. That is this representative. It's no proof here. It says machine learning algorithm. It minimizes over W some loss function, which is between the labels and a scoring function. Plus regularization. So this is the objective, and this is the regularization. This is what we've seen in both regression and support vector machines. In regression, this loss is y minus the f squared, right? The squared loss. In support vector machines, is the margin. And in here, the penalty is a regularization penalty, like L2, L1 norm, whatever we have. So in general speaking, this is a computation between the prediction and the output, and this is some constraint we have on the coefficients of the problem. Right? So then, assuming we have some weak general conditions, again, we're not going to worry about that now. Then in here, W is some overall data point alpha I, y I, x I, which is exactly what happened to the support vector machines. And alpha i's are the dual variables. So I can express the same problem. So if I replace W with, what happened in support vector machine, if you remember, we got to this form by differentiating the objective. We differentiated the objective, we set the differential to 0, we got this equation, and some other equations. But then, how did I get the dual problem? I replaced W with this in the primal problem. Right? I replace whatever f was in there, with this, and I've got my dual problem, right? So I get the dual problem. This is the primal problem. The dual problem is minimize the loss of y versus f of, now I have sum of alpha I, yi, xi, and x plus the penalty of sum of alpha I, y, xi. Of course, I have to do a lot of operations here, manipulate those things, and I get my goal. So there's important things about this transformation. One is, like in support vector machines, it gives us a way to actually solve the problem, right? In everybody who does SVMs will solve the dual problem. Nobody will attack the primal problem. So one interesting thing, good thing, is the dual gives a procedure for optimization. Quadratic solvers, SMO, so on and so forth. Two, if f is linear, which is a lot of machine learning algorithms have a linear function here, right? Perceptrons, regression, logistic regression, support vector machines. The actual prediction, once it's all said and done, it's a linear function, right? Sometimes with an additional transformation, like a sigmoid or a neural network is not a linear function, it has linear, some ReLU sigmoid, another linear, but a lot of the components are linear here. This theorem works for nonlinear functions, but a particular case when f is linear, it means what? Who is f of w and x if it's linear?
Line or?
It's wx plus b, right?
Yes.
If it's a linear function, it takes the coefficients times x being a vector, of course, plus b. So what happens when this is linear? Now, w, it's still this. So it means who's f then? It's the sum of alpha I, yi, xi, that's w, times x plus b, which is sum of alpha I, yi, then there is a dot product xi, x here, plus b, right? Because you can see how this works. Alpha xi, xi gets dot product with x. So my point is, this is the kernel trick. When you say kernel trick in machine learning means, now that I have a linear function, and I know w has this form, I can try to replace in here xix, which is the basic similarity function we have, right, the dot product. Replace that with some of these other kernels, RBF, polynomial, string kernel, whatever I want. So the kernel trick will be, if those things are on place, I can replace it. So using a kernel now, into my f, I get f of wx is the sum of alpha I, yi, kernel of xix plus b. Of course, this is just the linear kernel right here, the dot product. I'm saying, since I have this form, I can replace that with some other kernel. And then my linear algorithm, my f, which was linear, can become a non-linear classification now if I put, say, quadratic kernel or RBF kernel in there. That's a very typical move that was the essential machine learning for the past 10 years. Up to neural networks. So before 2013, when everybody started using neural networks, in no small part, the drive to neural network was not theoretical. So I'm not saying neural networks are better than support vector machines. Neural networks were driven mostly by the industry because they're easier to implement and deploy and scale. So it's not like they're much better classification than support vector machines. It's that from a Facebook perspective, it's much easier to deploy these networks, or even Apple now, with the iPhones have a neural chip in them, right? Or Google, they can deploy some large farm of computers with proper hardware, run them fast enough, get good enough results it's not easy to deploy support vector machines at scale. So then I think that was a big factor in moving the whole machine learning world towards neural networks. So up to 2013, this was what everybody was trying to do, big and small players. After neural networks, I think this kind of slowed down. Yes?
But there is such a fancy term like sequential, LSTM, blah blah. Can we do the same in SVMs? The things that we do in neural networks, can we do the same in SVM or other?
I don't have an exact answer for that, but
Uh-huh.
I think we can design a kernel that takes that into account. So
Uh-huh.
obviously for text, LSTM, right? You would have to have a representation richer than say unigrams or bigrams. Because long short memory, right? Like if you need to know something about the sequence of text. If I have a unigram representation, I know how frequent a word is in text. I can make up the last 5 words of the sequence. The idea of LSTMs is that a lot of what can be predicted next in text is related to the last 5 words in order. So I need to know something about that order. That comes down to a feature representation that allows me to do that. Just unigrams and bigrams counts is not enough, right? And some way of kernelizing that thing. I think there is a kernel to do that, I'm pretty sure. Now, I don't know if that works as well as LSTMs. Again, I think the issue with machine learning is that these big companies, they have a lot of data. They don't have the problems that we keep talking about of feeding not enough data, but they have huge amounts of data. So it's very important for huge amounts of data to be able to scale your algorithm. Even if this or some boosted decision tree does very good in theory, if I can't scale it to 1 billion documents, a neural network is going to win because a neural network will learn from 1 billion documents and my algorithm cannot use 1 billion documents. So there is another branch of machine learning that you should know about, but we didn't talk about. It's extreme data. So that has to deal with how do you do anything if you are Amazon and you have to deal with like billions and billions of things quite fast. So at that stage, it's not even the performance of the algorithm that matters. It's only scalability, right? So people have looked into sublinear methods, right? How do I train something that takes less than linear time of the data? I don't care about its performance that much. I mean, it has to be reasonable, but I'm more interested in run through all the data. And so the constraints of industry are mostly on how to scale to the data that I have. So anything that's say a quadratic, right? N squared running time. It's impossible, right? N squared running time. But if I have 1 billion things, N squared, it's just not acceptable. Right? So I think the main concern is that. Now, the LSTM have a very specific form which is very useful for text. Because it turns out in text, to go back to your question, once I have 5 words, I can probably 90% accurately predict the 6th one, independent of the rest of the text. Right? Most of the time, I can tell what word comes next. That helps a lot translations, for example, completions. All right, so then what I want to do now is show you some intuition about perceptrons and then talk about regression. So I'm done with support vector machines. I want to talk about kernel functions in the presence of other algorithms. So I think we started talking a little bit about the perceptron, how that goes. I want to do the perceptron without the representer theorem, just to create the intuition for you to see what this actually means. So anybody remembers how this goes? First of all, we were all training set will make it yi equal 1. Remember, was that thing when we say, effectively we're saying if yi is -1, then move the point xy into the point -x -1. Because from the perspective of a perceptron, this would be the same point. If you classification plus minus, classifying this point here as positive, it's the same as classifying its reverse as negative. Right? And then, anybody remembers the algorithm? Init W equals 0. The task of the perceptron was what? To classify all points to the positive side. So that means Wx has to be positive for all x. That was my plan. And so I start with the W equals 0. And then, what was the loop? How did was it kind of a gradient descent thing? But we didn't derive it for gradient descent. We did a little bit of geometry. We say, if x is misclassified, that means Wx is negative, then do what? We can derive this update from the gradient descent idea. If you look at the perceptron loss and you differentiate that, this would be the gradient descent rule. So perceptron served us as a pedagogical example, but we don't use perceptrons, right? But gradient descent, we took the loss, differentiate, get the gradient descent update rule will be this. Now, we also did this with geometry. Remember we said, here's the plane, here's the misclassified points. How do I make that plane get the point on the other side? Well, if this is the normal of the plane W, and my vector is misclassified, that's my x here, how do I bend the plane to put x on the other side? If I add W to this vector, I add x to it, that the normal is going to move, the plane is going to move too, right? That's what we said. Good, so that is the primal problem in perceptron. That's how we did, until I think we say do that until all the points are correctly classified. That means all the points have Wx bigger than 0. That means there's no misclassified points to do updates with. The loss would be 0. Hands up, who's with me? Good. Now, is this satisfying this thing here? I think it will. We have to figure out how do we write it this way, right? But then we're gonna get some W that's a linear form of the data. This is the data points, the labels, and the coefficients. Right? So I could try to do that. I could try to say, okay, what's the loss? It applies the theorem, get a W. But I want to do it kind of like baby steps without this theorem to see if I get there. What is going to happen here? We have a guarantee, a theorem that we proved in class, that this is guaranteed to finish if data is separable, right? So we know there's a finite number of steps until it finishes. Of course, it will never finish if data is not separable. If there is no plane that separates, there always going to be some misclassified points, so I can hope for that. So for the perceptron to do it in a conceptual way, I need data to be separable. If data is not separable, I can still use this, but then I'll have to have some criteria where to give up, right? Because it will run forever. But if data is separable, this will finish. I want to rewrite what actually happens here, right? I'm going to say, how about mi is the number of times the point xi is misclassified and used for update. The reason I'm saying it this way is because if I have several misclassified points, I'm picking one of them. And it's not guaranteed that the others will be picked later, because once I move the plane, maybe some of these misclassified points get classified correctly now. Right? So at every round, I'm only picking one point. I'm thinking in a very like baby steps conceptual analysis here. Every time I run this loop, I pick a point, I add it to the plane. So now I'm counting at the end how many times I pick each point. Of course, some of them will be zeros, right? Because some points are not going to be misclassified from the beginning. They're never going to be misclassified. They're never going to be part of the update rule, so they never get added to the plane. Right? So for every point, I have this count of how many times I use that point to update the plane. It's also possible that the point updates the plane more than once, right? once I add a point to the plane, I'm rotating the plane, I'm not guaranteed that that point is classified correctly. So I may have to add it again and again, and that's how we prove the theorem. We're saying if you add every point enough times to this plane, eventually all the points are gonna be correctly classified, but for some of them you may need to add them quite a lot, because the more you add them, the more W becomes aligned with X, right? Because it's NX, 2X, 3X, 4X, the more you add them, the plane is gonna bend to include that point in the correct region. So now, who's the plane at the end? Final. It started with 0, right? And then I added each point mi times. So who's gonna be? 0 plus some of the updates, right? For each update, I get xi, but a point can be added multiple times. So this can be written as 0 plus sum over all the data points of mi times xi, right? That's saying, instead of looking at one by the time, I can group it and say, how many times you add x12 to it? Well, you added 4 times. So then you get 4, that how many you add. And the ones that are not added will have a 0 here, right? Easy. So that, of course, is sum of mi xi. Is that also sum of mi xi yi? Can I just add a yi in here? Yeah, why? Why is that? Yeah, all of them are 1 because I already deal with that problem. So if I wouldn't do that in the beginning, I can probably do the algorithm without that trick. I lose the visualization aspect because if I put all the points to one side, it's easy to think, how do I turn this plane so that side is in the direction of the normal? But I could probably run this algorithm with some modification without that. Just be careful how you deal with misclassified points. And then the points that are subtracted, there'll be the negative points in here. They will always be subtracted to xi times minus y, so I can get the same thing. But nevertheless, that's correct if I do the transformation at the beginning. Does it look like this representative theorem? Doesn't it look like W is a linear form of the training set? Of course, my alphas in here will be who? These m's, and these are the dual variables. Yes.
If you actually do this problem, like solve the dual problem to get a Rosetta, do you have integer alphas?
I don't know. Maybe what I think happens typically in those problems is that there is a discretization of it. So even though the dual may produce real alphas, there is an integer approximation of that would give a good enough plane. Because this procedure stops when everything is correctly classified. So say an alpha or an m comes out 5.4. That probably means once that's 6 or so, it's going to work out. That's my guess. I don't think by doing the optimization we can guarantee integer alphas. Yeah. That's not what I have.
Well, maybe if you have alphas, but they're rational alphas, just scale them up a little bit.
Sure. So I think there's some approximation to do so. The perceptron, again, it's something that we use mostly pedagogically to make a point in different parts of the course with it. And here with the kernels. So can I use the kernel thing in here? The kernel trick. Once I know this W is the linear form, what can I say about the classification? So how the classification of a perceptron looks like? It's F is Wx is W times X, right? So that will be sum of mi xi yi x. So that's sum of mi yi xi x dot product. Same trick, right? So now I can replace this with the kernel. So I could run a kernel here, and I think if I do, say I put a quadratic kernel, or an RBF kernel, that's Gaussian form that we've seen, I think my classification won't be linear anymore. I think if I look at that, plugged in that kernel in, which is not a linear dot product anymore, I think I'm going to get the perceptron to do non-linear classifications. In fact, I'm sure, because that's in your homework 8. There is some data set that's generated artificially by us that clearly cannot be done with a linear function, linear perceptron. In fact, it's pretty close to 50-50 no matter what you do there. But once you apply a kernel and you plug in the kernel into your perceptron, out of a sudden, boom, 100% accuracy. Yes.
So will the plane in the original space be a surface after a kernel?
Right, if I look at that phi mapping
Yeah.
that we've seen, which again, we don't want to do that explicitly, just for theory purposes. Right, in the original space, we don't get a plane. We get some quadratic surface or whatever the kernel is. If it's RPF, it isolates these convex regions in the data. But then if you look into the mapping space, which you cannot really do because all those kernels are not explicitly on phi, right? We give 2 or 3 examples of the phi, but in reality, you don't use the phi. So if you look into that space, the separation is linear. So that's exactly what's going on. It's doing the algorithm, just not in the original space, in a different space. Yes?
So for this to happen, is it necessary that W has to be the combination of the dual?
This is the result of the theorem. If you have this kind of form and some mathematical conditions, which mostly are satisfied. So I'm not doing that theorem in detail. Then this is going to happen. So then I can apply this to the algorithms that I have.
And F has to be linear.
F doesn't have to be linear. So, but the kernel trick works very well for linear functions, right? Because the kernel trick requires you to replace this dot product here with something else. But I don't get the dot product. I mean, maybe I do get it to other functions, but the obvious case when I get this dot product here is when this is linear, right? If this will be some other weird classification from like a decision tree, I don't get xi times x. But in linear form, where this is w, I'm always going to get a dot product here. I always can replace that with a kernel. There is a part 3 of this, which is important, which I mentioned many times during the course. The primal versus dual has a lot to do with moving away from instance based. That is, if you look at the primal, you have some constraints on classification purposes. And the way you handle the objective regularization, you address X by the representation. You know, if it's a document, it's feature values or images or span, right? When I say X, I mean the vector of feature values for X, right? Notice that in the dual, we don't actually need X ever. We don't, what do we actually need? We need K of X, I, and Xj, right? So if you look at the dual problems, so I'm going to say here X, the primal problems require a handle of vectors. Whenever you say a document, an image, a patient, whatever data is, for a primal problem to work, the way we did regression, you guys remember the normal equation xt, x at -1, right? We need x, right? The way you do the decision tree, you look for feature values, that means you look at x. Dual problems don't need x directly. What they need instead? A way to compute the similarity between 2 patients, 2 emails, 2 images. And this theorem effectively says, in most problems, if you can compute the similarity very well, say you have a divine function that just does the similarity for you, you don't need to worry about the representation of the data. You only need to worry about knowing who's similar with who. Like if somebody can tell me for all patients in the world, what patient is close to what other patient, like numerically, I don't need just to know that patient is close to that. I need a similarity value between the patients, or between images, or between documents. If I have this, I don't need to worry about how do I represent documents, bigrams, trigrams, feature values, so on and so forth. Now, of course, that's what I'm saying here is magic, right? I mean, you could ask, wait a minute, how are you going to get similarity if you don't have bigrams and trigrams and whatever? I'm only posting this as a philosophical argument that if you could get similarity, then you don't need to worry about representation. So to make it non-philosophical, is it possible, can you give me some examples speculatively where where I may be able to get similarity easier or better or more reliable than I could get features? Can I think of some data sets where data points, objects, where it may be hard to get the features correct, features that I need. I mean, I may get some features, but not the one that I need for my problem. I have glue on my hand, sorry. It's gonna be on camera. But I could get a similarity between them. In other words, if my representation is weak, meaning it's not that well correlated with the features, both may suffer, right? But I may be do better with the similarity, more reliable than I can do with the features alone. Can anybody guess some data where that might be true? Images? Can I be more reliable than, say, two images are similar than to obtain a feature representation? I agree with some caveats. Why would that be for images? How many people did the hard features? Yeah, do you think hard features will work for general images? Like suppose I don't do digits black and white, 1, 2, 3, 2, 9, right? Suppose I do, pictures taken in Africa. How many hard features you're gonna need to do that? The problem with image feature representation, it's difficult to obtain good features. So people in graphics have looked at a lot of, segmentation, right? Can I cut out tigers and plants and cars out of the image and detect I have a car? And with that detection, which is pure graphics, is not machine learning. If I know I have a contour, then I can classify the contour and I say, okay, I create a feature, this image has a car in it, but it requires segmentation, which is not an easy process, right? So now, of course, we use these convolutional neural networks that look at a lot of chunks of the image, and the biggest difference versus hard features is that neural networks can match this chunk on the bottom right corner with this chunk on the top left corner, which you guys cannot do with hard features, right? Once you cut that rectangle, it's nailed to that region. So if I ever have a 7 in here versus a 7 in here, I can't move my rectangle. But neural networks convolution net layers will do that. Will say, okay, you match this part here with some other part there. But that's extremely expensive and kind of hard to get. Convolution neural networks are not an easy thing. So you can see how general images might have a lot of problems with feature representation. Pixels are pretty much useless, right? If my image is 3,000 by 4,000 pixels, I get 12,000 pixels with 3 values each. There's no point now going pixel by pixel and write down feature values. I end up with like something like 30 million numbers. No algorithm will be able to make anything out of that. So I need either some graphics things to go by, like contours and cut out objects, or hard features, or convolutional neural network. What I'm saying here is that this is not a trivial thing for images in general, but similarity might be. Can I get similarity to work for me, for images? Right? I mean, I have the same problem, right? How do I measure similarity? In general, this problem, like I said, philosophically, is when you get down to earth, you say, like, how can you measure similarity if you don't have features, right? I mean, so if similarity requires features, then I'm back to I have an X and I can deal with the X, right? Yes?
So can this be applied to something like words, where words appearing in similar contexts are similar? So even if you don't have good representation for words, you know which words are similar in the appearance.
Sure. So what he's saying, using a context, what's around, that's the idea of word vectors, right? Which we didn't do in this class. I used to do it, but now everybody's doing word vectors, so you're gonna hear from them anyway. You can't escape word vectors. Yes, the co-occurrence, right? If I look at what's around me, and if two words appear in the same context, then I measure similarity that way. I don't need to know that word, what it is, because I can know what other words are around it. So similarity can be purely a function of context. That's actually quite powerful, not just at words level. Just in general, tell me who you hang out with, so I tell you who you are, kind of thing, right? If I know your friends, I can probably, by looking at everyone's friends, can I tell who's similar? I'm Facebook, right? So I don't know who's similar with who, right? It's hard for me to look at the person. In fact, there's all those privacy new regulations, and there'll be a lot more regulations on privacy. The next 5 years will be about Facebook privacy, you'll see. And then Facebook will have a harder, and not just Facebook, the people they sell the data to, they'll have a much harder time accessing your direct features. Who you are, where you're from, what you're doing, cookies, what you're buying, what you're selling. It's gonna become harder and harder. So I'm Facebook now. Can I do this instead?
Well, looking at the friends, it's the
Right, if I look at the friends and I say, you and me have the same friends, we read the same posts, we read all that, maybe I can come up with a more reliable function than trying to create features. And remember, this only requires a calculation, so back to the kernel idea, we don't need that phi function. As long as we can estimate this somehow as a similarity function, symmetric and semi-positive definite, then we can plug it into all kinds of machine learning calculus. What else? Let's move on to the original idea. Can you give me an example of data where extracting features might be problematic, but computing similarity might not?
Videos?
Videos? Videos, like YouTube videos? Okay, so he's saying extracting features from a YouTube video might be tough, but comparing two YouTube videos might be easier than extracting features.
same problem as image. It's not going to be easy to calculate the similarity between
I mean, that's the data science problem, right? If you go in industry, again, like I said, the data problem is when something that's off the shelf doesn't work. You have videos. How do you compute their similarity?
Can we again use something like collaborative filtering where two people are watching the same kind of videos?
Right. That always works out of context, right? That's always a good baseline to start. I don't want to go into videos and figure out frames and where they stop. What I'm going to use for similarity is who's watching those videos. And if the same people watching those videos, I don't even want to know what's in them, right? I just say they're the same because the same people are watching them, right? But there might be ways to compare videos. I don't know anything about that, but there might be ways to do that. Other examples. How about not videos, but movies, as in Hollywood movies? Can I compare movies better than representative movies?
Again, who works in context-based knowledge using context.
I'm Hollywood now, and I'm gonna estimate box office. Can I look at movies and say, it's hard for me to write down the features of a movie, but it's easier to compare to movies to get some similarity function between them? Yes.
Again, apply the same logic.
Yeah, the collaborative filtering, which we might talk a little bit about next week. If I have a rating matrix, I don't even need to know what's in those items, movies or books or papers or whatever it is, right? I can just say, I know who's watching those movies, same people are watching them, they're similar. But what if I don't go that route?
You can just say when the movie was released, so if the movie was released in the summer, two movies are released in the same summertime, the same month, there's no...
Okay, the movie release. I think the movie release is kind of a weak indicator. I wouldn't go that strong. But
The actors and...
comparing kind of what I know about the movie with the release day, like Valentine's Day, romantic comedies, right? So to speak, maybe I can get a similarity function that's more reliable. In fact, I think for media items, movies, books, songs, this is typically more reliable than the extracting features. Like in a song, You can look at this spectral, acoustics of, piano and whatever it is as features, but comparing songs to know, okay, what songs are more similar or more dissimilar to each other, it's probably an easy job.
When can you not use the theorem? I think everything can be represented like that. All the things you've done.
I'm not sure that everything can be represented like this. So, like for example, a decision tree.
Yeah, parametric methods
Right.
should work, right?
Yeah, I think a lot of things can be represented this way, and there's some mathematical conditions that are required here. But I think maybe something like a decision tree that chops the data very irregularly, because decision tree is just driven by the points. They're not driven by any, say, linear shape or assumption. That would be hard. That's my guess right now. I have to think more about this answer. Yes.
So with the example of like songs, wouldn't you still be extracting features to like calculate that similarity?
Right, that's the connection between philosophy and reality.
Okay.
He says, okay, that sounds all good to me, that's what he's asking. That's, I believe the theorem is just how can you possibly compute this if you don't have a vector representation of X? So that's what we'll be talking about. One answer is context or collaborative filtering or click-through data, which is saying, I don't know anything about those songs, but I know who listens to them. And if I know who listens to them, I can easily compute a similarity based on dot products between who listened to them and what rating they give and something like that, knowing nothing about the actual songs. What else can I do with songs? So not who listens to them. I don't want to extract features, but I want to compute a similarity as opposed to a vectorial representation. That's extracting the feature, right? When I say genre or author or something, that's essentially extracting a feature value. So it's similar to the context of who listens to them, but not exactly that. I'm not looking at, okay, here's my songs, here's my users, I have a 1-0 matrix who listens to that song. If you look at playlists, you're Spotify now. Everybody has playlists, millions of playlists, right? Can I tell from playlists? I'm not looking at who created the playlist. It's just I'm taking playlists. Can I look at a playlist and say some songs are similar or not? Do you think?
Yes.
I think I should be able to, right? Play with this idea of context. Hey, everybody who listens to those 3 songs also listens to this one. I don't know who the person is, but looking at a lot of movies don't have playlists. Usually people don't think of I'm going to watch 7 movies in a row, right? It's only fanatic people do that. But usually for music, I get these playlists. Everybody has playlists, right? And then from playlists, I may be able to easily tell what songs are similar. Actually, I know people working for Spotify, and all their research is based on playlists. All their, what songs to recommend, what songs are good, what songs are worth promoting. It's based on playlists, looking at people's playlists.
What do you do if there are different notions of similarity? Because you mentioned playlist, right? Now,
Say again?
What do you do if there are different notions of similarity and you're comparing one notion of similarity with different? So, example, you mentioned playlist, right? Now, there can be a playlist like 90s playlist. That 90s playlist has different genres of music. Songs that are not related, but they are related in terms of one thing, but not another thing. And where they are sorted by genre, as he said. It's all romantic songs. They are not from 90s, they are from 90s, 2010s. So how do you compare those two?
Right, so that's a much more general question that he's asking. This theorem says that what you can do here, and this is a global real function. It says for any 2 items, it's going to give you a value pair. Right? And he's asking, is there a consistent similarity value? What if there are notions of similarities that are different notions from the point of view of a user, those things are similar, and those 2 things are not similar. But from the point of view of, say, of a music producer or an artist, those things are not similar at all. How do I represent that similarity when I only have one real function here, right? And I have 2 items. This is a massive, massive open research question in machine learning. And the view is, theoretically, we know what it is. We know the problem and we know the answer. We need a multidimensional similarity, right? If I represent this function not as a one variable result, but as a, here's a space where I have similarities based on different criteria. The problem is the theory doesn't work that well with a multidimensional similarity. So as you keep going into this direction, there's something called ordinal embedding. Ordinal embedding would take no features at all, only who is similar with who in an ordinal sense, not even real values. Would say this movie is closer to that movie than to that movie. It doesn't say by how much, it just say closer. And then it says that patient is more like this patient than this other patient. So it gives you all kinds of orderings. And it is well known that those orderings, if they have inconsistencies, we can't represent it in a unidimensional space. So we need more dimensions. Okay. So this is the basic case where this similarity is unidimensional. The solution to your question, in theory, is a multidimensional similarity, just the whole thing has to be reworked. And moving from dissimilarity to multidimensional is extremely difficult mathematically. It's like from 2SAT to 3SAT. 2SAT is a trivial problem, 3SAT is impossible. Same thing happens here. As you increase the dimensions of this whole concept here, stuff breaks down immediately. Things become NP problems, the geometry doesn't work anymore. In high dimensions, we also have the problems that, geometrically speaking, objects like cubes or balls, I don't know if you know this, but in high dimensions, those things tend to have very small volume. So the more you increase the dimensions, any object will have very small volume. So in terms of the whole convexity argument, it's much more difficult. So we don't know how to solve that problem, in short, but it's a real problem.
For a given problem, can't we predefine the categories we want to calculate the similarities for?
Right, we can break the data into smaller pieces and do it separately for those pieces, especially if we know the categories in advance for the test, right? Like we split the movies into action movies, comedies, and so on and so forth, and that's easy to tell in advance, so we just applied that. Same thing like splitting the patients based on category. Here's a patient that has diabetes. We don't need to classify diabetes because we know his problem is diabetes. We need to classify something much more detailed. So we can only compare this guy with the other patients who have diabetes, right? So we can break down into parts. This is a little bit of drain engineering. Once, as a big company or big hospital, you decide to break into categories and further split and further retune your parameters, then you need to hire an engineering team of more and more people. The more you break down into parts, the more you end up with floors of machine learning engineers. Google has 3 floors in New York alone of machine learning engineers because of this reason. Yes?
If you're not extracting features and relying only on context, and it's something completely new which no one has seen.
That's another well-known problem, right? If I use click-through data to predict what documents are relevant, I'm Google now, right? And I don't even read the documents, I'm just gonna answer, I'm gonna post the links that everybody clicked on before, right? Because the moment I say, I don't know, Donald Trump just fired the DHS secretary, right? Already that has been asked a million times. Already people have clicked on a million documents. If you ask the same question, I'm going to produce that. What if somebody asks a new question? Same problem, right? So I can't do that for a new question. But similarity might still work, right? I mean, if I rely, you write about this idea of context and collaborative filtering. Nobody has any reviews for this movie. I can't go by what other people have said. But I can still compute similarity between this movie and other movies, maybe, somehow different.
So you'd have to rely on some form of feature extraction for that.
In reality, you probably want to look at the combination, right? I have to know something about those movies to compute a similarity function. But that may be, if it's a new item, I don't know, but if it's in a list, or if it's in, published in a certain way, or if it's by a certain author or something, that may give you an idea of how to compute similarity. And even if I get features, it might be easier to do this than trying to detect how well those features are doing for my particular machine learning algorithm. Like if I do feature selection, for example, or I don't know if I should run PCA or not on these features, but I can figure out the similarity function. A lot of this also comes down to domain expertise. The best way to do as a data scientist when you run into this issue is to talk to domain experts. If it's patients, talk to a doctor. Hey, why are you predicting different medicine for this person versus that person? Because to me, they look the same. I work in consulting, machine learning for medicine, and this is one of the most typical questions we always go back and ask. Not just doctors, nurses, coding, all the medical people. We look at documents and say, those two people look the same, but yet they've got different drugs, they got different treatments, they got different that. Why is that? And they always have some things that we, the machine learning scientists, are like, are you kidding me? Like, okay, I knew this guy from before. It's not written in his note, but I treated them 5 years ago for something else. That's why I predicted that medicine, right? So then we kind of, give up because we don't have that information anyway, so it's not a fair game, right? Or I talked to him, it's not in the note, but I talked to him about family history and all that. Now those things are in the notes. There's also not the doctor notes, which we typically have access to, but things like what they said before coming to the hospital. I have pain in my left shoulder, things like that. That also may drive some of the treatments. Some of the things that we don't have access to because the regulations, the laws, is insurance rules. They don't write down what insurance requires in terms of billing and codes. Like sometimes the doctors can't put a code. I mean, they have to have a strong justification to ask for an expensive code. Otherwise, the insurance will come back and say, why are you asking for so much money? Justify it. So insurance will not, you know how it works with insurance in healthcare? They will not ask for small things. If a doctor said this is a small thing, it's a cheapy code, the insurance will just pay. But if you say this guy needs a heart surgery, they will be like, okay, you have to explain to me why that is. So sometimes these are things that are not explicitly written. Doctors are not allowed to write those on the notes, yet they matter a lot in terms of the final predictions. Okay, what else? So enough of this then. Back to the philosophy. If you know the similarity function, if you somehow can compute this exact, that's equivalent to solving the machine learning problem. So having a good similarity between your data objects, or a very good similarity, it pretty much solves the problem. And that's very related to what we're going to do next. This KNN idea that we didn't talk about here, but we're right. Everybody knows how KNN works, right? I look at the test point. I do no training at all. I look at the test point and I say what? Look at the points close to it. And if there is some majority or uniformity in terms of labels or predictions, it's easy to say this patient, what disease they have? Well, it has the same disease like the other patients that are similar to it, right? Hands up who's with me on that. We all heard of KNN, right? That is a very easy algorithm, but it relies on knowing what are the correct neighbors to look at. Right? If I know this, if this works perfectly, if this will put a patient exactly close to the other patients like him and far away from the patients not like him, then it solves my classification problem right there. Right? So I can just say which are the similar patients to those patients, predict their labels, and I'm done. Okay, so to finish this up, how would this work for linear regression? How would this whole stuff in here work for regression? This theorem. Oh, just before I do that, what other algorithms than KNN relies very heavily on these similarity functions? Algorithms that we don't do in this class because they're not supervised. Clustering. The success, alive or dead, of any clustering algorithm is this function.
Any cluster.
Yes. I mean, there's many types of clustering. There's density-based clustering, k-means-based clustering, fancy hierarchical clustering, on and on and on and on, right? All that's very good, but they all need a similarity function between the data points. And if you have a bad similarity function, clustering won't work. So all that unsupervised, not just clustering, but the whole unsupervised track, which you typically do in a course like data mining techniques or something like this, requires some notion of, okay, who's close to who in data. So regression, that's the least squares. What is the objective? Let's write it here, objective. Is it minimum of W, minimum over W, is that it? So this is the objective here. Actually, let's write here objective. And what is this term? L2 regularization. Is that gonna fit in this? Clearly it fits. So then I know W has to be sum of alpha I, y, I, xi. Right? And then how do I get the dual? I'm going to write it down and then we can look at it. Is that true? It's easy to see, right? All I did, I plugged in this W into the main objective. So this term here corresponds to the regularization, and this term here corresponds to the square loss. Right? Of course, I have to, now, I'm not going to do the manipulations in here, but this is a dual form. Instead of finding W's, that's the primal objective. In here, I have to find the alphas. And the conditions of this theorem are very similar with the KKT conditions. So it will be some conditions on alphas and how that works. But apart from the engineering, which I'm going to skip here, I think it's an extra credit in your homework. If you really want to go this route, you can try to do this and get exactly what conditions you need and how to actually implement the dual regression. But apart from the engineering, what about this? Is this working out for me now? Can I plug in a kernel into this thing? Let's answer the question first. Can I plug in a kernel here? Can I replace the dot product with some quadratic kernel or string kernel or RBF kernel, whatever I want? Yes. You see the dot products? So what's the hope in doing so? Why would I do that? Yes, yes, but that's not the ultimate purpose. Increase dimensionality. I get a regression that's a non-linear classification. Of course, I have to guess the kernel. Remember, in those kernel methods, I can try to ask the algorithm to give me the parameters, but I have to tell it I want an RBF kernel. Okay. So that's an extra credit in the homework. If you want to try that, can you run regression on a very non-linear data set, 20 newsgroups maybe, and see how it does?
In the support vector problem, SVM problem, we were maximizing the dividend. In this and we said that maximizing the dual is same as minimizing the primal because of the saddle point. In this, like, we are minimizing.
This minimizing or maximizing comes down to engineering. So the reason we maximize is because we have some negative signs in there and we swap the sign and we get the maximization problem out of it. So you still have, the principle is the same. Plug in the W into the objective, see what you get, and you still minimize it, but now if I get negative signs in here, I can swap that into maximizing. Okay. So that's just pure engineering. I still have the same objective, derive it into the dual, and now the dual may look in a certain way. I could say minimize minus the alphas, right? But I mean, maybe you mean something else. It has to come down to that saddle idea. So the KKT conditions to work, everything that was one way on the saddle this way, the other way would be this way. So it will come down to a maximization of the curve, right? To have the saddle conditions have the KKT condition, just a different name. So to have the saddle point dual close to the primal, one side of the saddle has to be this way, the other one has to be the other. I don't know, maybe that's what you meant. Okay, how about logistic regression? Means the problem is a different objective, right? What is the objective? It's the probability of a class given the coefficients and the data point, right? The correct class. In logistic regression, this is 1 over 1 plus t minus yi wx. I'm skipping a lot of the transposes here. Like I said before, you gotta do the dot product in the right way, right? So if that's the case, the objective is to minimize over w. This is still a square. I think this is still a L2 regularization form. Plus sum right for 1 to n of logarithm of 1 plus t minus yi wx. Where did I get this?
Derivation.
So normally in maximum likelihoods, how do we look at probabilities over the set? This is for 1 point, probability of the correct label for that thing, right? Hands up, who's with me? We all remember logistic regression? This is a particular logistic function. It's given to us. We don't choose that. It's a fake probability that says that's the probability of being correct here, right? But then when we have probability, maximum likelihood says, how do we maximize the likelihood over the entire training set? How do we do that?
Summation.
Not summation. If we assume the data points are independent, which we always make that assumption, the probability of being correct to the whole set is what? Is multiplying those probabilities, right? But we don't like multiplication when we do mathematics. That's what's required. Instead, we do what? We take the log, and then we end up with a sum. That's the maximum likelihood idea. So what happened to the 1 over? Where did the 1 over go?
Some negative sign became positive.
Huh?
Some negative sign became positive.
This is 1 over inside the logarithm. It's minus the logarithm. So I had a minus, which I didn't put. I still put a plus because what? There's no minus here.
No, you're minimizing it, right?
Minimizing, right? So I'm supposed to maximize the likelihood, right? Likelihood, the probability of being correct has to be as maximal as possible. It's a product over all data points. 1 over becomes a minus, but then instead of saying minus something, maximize that, I say plus, minimize that. Back to the question that has been asked before, how did you get the maximum on the other way? I do the engineering and I still have, instead of maximize minus something, it's minimize plus that something. All right. So what do we get if we plug this in the dual form? Again, W is the sum of alpha I, xi, yi. Minimum over alphas. Number 2, sum of ij, alpha I, alpha j. This is the same, right? Again, this is the dot product, right? Linear kernel. Plus sum over j equal 1 to n. Logarithm of exponential of minus j sum of So easy to see what I did here. I just plugged in this into the equation. Right, don't plug this W. But once I have the theorem, again, I can apply it, get these dual forms, solve the dual forms. There's advantages in solving the dual form. One of the main advantages in SVM, most of these alphas will be zeros, right, down to KKT conditions. KKT conditions, their power is exactly in that little detail. I have these constraints, which is the classification constraints. Wx plus v has to be bigger than 1 plus the slide variable. The point of KKT is everything that's not an active constraint that's satisfied with room to spare, the point is farther from the margin than it needs to be. We'll have an alpha equals 0. So the magic of these dual variables is that the constraints that are kind of obtained for free, or you don't need to enforce them because they get enforced by the other constraint. There's a transitivity. It often happens when you have a lot of constraints, right? Then you don't need to worry about those constraints, and the KKT puts an alpha equals 0 on them, says, this is not important for me, this constraint. You can do the whole optimization without that. You're gonna see this in linear programming. If you ever did an algorithm course, linear programming, when you have all of these linear constraints that enforce the solution must be here, in this region, here, here, you get some constraint that's satisfied for free sometimes, right? Is that that region that's being enforced by the constraint, it's already part of this, all the solution was in there, so we don't need that constraint. So KKT kind of does the same thing here. In here, just to follow the analogy one more time, some m's will be 0, meaning the point was never added to the plane. I didn't have to worry about that data point because it was classified correctly from the start and it never got misclassified. So that point effectively never updated the plane, which means if I take that data point out of my training set, I would get the same exact plane because that point never held. I want to make a final comment about this philosophy, which is the biggest difference today between data scientists. If I would be a recruiter, which I ask many, many times to serve as a recruiter for many companies, I never serve as a recruiter because I'm not interested. But some of my friends, people like me, are recruiters. So we constantly discuss interviews and what to ask and what to not ask and what students are prepared for, so on and so forth. So I talk often with recruiters. I've never been one. The biggest difference at this level, you know, I'm graduating master's student, you know, I get a job in data science, is the ability to look at all this, not just this, everything we've done, beyond the mechanics. Okay, I can download the package, run it, I get weights, I get precision, I get accuracy, I get regularization, you know, the whole pipeline thing. Most people can do that, right? This ability to understand, okay, why some alphas are 0 in this case, or why these m's are 0, or what points are useful for me, or what points are not useful, or what points are breaking my algorithm, or what features are necessary, when to run PCA, when to not run PCA, when to run a different feature selection algorithm, when to apply a kernel. and when to not apply a kernel. Ability to think of those things. Of course, you are very, very early on in your data science career. You cannot compare yourself with, Cheng or Bingyu who've been studying this for 5 years. But some people would have the ability to think about those things, and some would not. And there's enough machine learning scientists, data scientists today to choose from. 10, 15 years ago, if you're a data scientist, you're hired, because there were just not enough data scientists. So we have to hire all of them. Now we do. So it's not like everybody's automatically gonna get a job. Sorry to put it that way. You need to have an ability beyond running something, get an accuracy. When you came to office hours and you were like, I run my code, hands up, I don't know what to do. Of course, that's the purpose of office hours. But you gotta go beyond that point in order to succeed in it. All right. So it's absolutely worth time to think about those things. Not just today. Whatever problem you have, whatever you want to solve, instead of trying to rush up, get an answer. Okay, why is it breaking? Because that's how you get some insight. Not to mention, if you ever want to go to grad school, like PhD, all your PhD will be about this question. Why stuff are happening in that way? Get an insight. All the research successful papers are driven by some particular insight about what matters. I've seen an amazing talk, and some of you were there, David Blake, who talked about confounding variables, something that's way beyond the scope of this class. But he talked about how if you run machine learning algorithms, quite powerful ones, some variables are so sparse in data. Like his example was an actor that only plays in Star Wars. Because he's the cousin of George Lucas. He's not really an actor. That guy is his cousin, and so he only get plays in Star Wars. He didn't make any other movie. What's going to happen if you run a regression comparing feature movies with box office target label? That guy, which is a total unknown, would have the highest weight in the regression, right? Because from the regression perspective, here's a guy who, when he plays in a movie, that movie makes gazillions. When he doesn't play in a movie, it's something else, right? So regression will output a huge weight for that person. That makes total sense from the objective and regression did its job. However, that clearly breaks, that guy is useless as an actor, nobody will hire him, right? So from the point of view of what helps box office, it's not useful. That was David Blake's example, and it's clearly an industry problem too. Now you're Netflix or Paramount Pictures or whatever. If you run machine learning, you have to be aware of what you're doing, right? So that kind of thinking and insight of how to deal with those things. Of course, his method is probabilistic in nature, studying confounding and relationship between those variables, and how to isolate the confounding variables with a probabilistic relationship with the other variables. But it needs some insight like this into what's going on first. How many people do you think run regression naively on movies and had this problem and never thought about what's going on here? I mean, how many people did movies with box office targets and actors in them? So many people right before us. And they didn't identify this issue until the year 2019, right? So I think that's what you have to worry a little bit if you are a data scientist. Okay, I'm almost done here. I didn't start KNN, but I will start it. I have 1 minute, 2, 3. Okay, that's exactly what they tell you, Pedagogy 101, don't do that, right? Don't start something that you can finish. But I'm not really starting KNN. I'm just gonna go into this idea of, I'm hoping Jay Aslam will teach KNN. If he doesn't, no worries, we'll do it on Tuesday. We all know the KNN idea. I mean, this is so trivial that people have heard it about in high school. And honestly, people have done KNNs from the classical time, the Roman Empire. They did KNNs, they just didn't call it KNNs.
We did KNNs in Fundis 1.
There you go. Yeah? So if you took Fundis 1 as an undergrad, you do that. Obviously, the idea is, this is my test point, right? What do? I look at its neighbors. To identify neighbors, I need this, right? What is a neighbor? Whatever is similar to that point. But if I have this actual distance, like a number, I could tell that this guy is a better neighbor than this guy, right? I could tell out of these neighbors, some neighbors are closer than others. And then once I identify the neighbors, how do I make a prediction here? I look at the neighbors and have some heuristic, majority, consistency, I don't know, whatever, average if it's a salary, right? I take those guys' salaries, I put an average. I think that's easy to see, right? What I want to point out, before we move into fancy KNN, that's the purpose of studying KNN, something called kernels and parson windows, which we're going to do separately. I only want to point out here there's two types of KNN. One type which is closest K neighbors. That's where the K comes in KNN. For everybody, I look at closest 3 things, 4 things, 5 patients. Or the other option is, this is called the neighborhood. So the neighborhood could be either the closest K things or everybody who has the distance. So the point is X, let's say Z. Everybody who has the distance, at least some value, right? Not distance, this is similarity. So this is based on strictly the top 3 neighbors. This is everybody who fits in a range. Everybody who's that. What's the advantage of this is everybody has 3 neighbors or 5 neighbors. The disadvantage is some of these neighbors will end up being pretty far away. The advantage of this is every neighbor is actually a neighbor, right? Because it's controlled by this value. I'm not declaring anybody a neighbor, at least its cosine value or Euclidean distance or whatever, it's at least blind. The disadvantage of this is some Z's will have no neighbors and some Z's will have huge amounts of neighbors. In a dense region, this neighborhood will contain hundreds of points, while in a sparse region of the data, I'll have no neighbors. So which one's better? That's a hard nut to crack, right? Which one's better? So with this, you can start the homework, you know. But we're gonna need more stuff, and we'll see what happens on Thursday. I won't be here. I'll see you again Tuesday. But if Jay teaches any class, in particular something that he likes, maybe not can, and I think it's kind of simple, it's going to be a nice lecture. We're going to try to record it anyway.
No, I think that